Good morning. Welcome to our third day of the Xendee University Week. Today is our International Day, and we already had a session early on about the Middle East. Now we're switching more into Europe. And the first presenter we have today is Michael Niederkofler. He's going to talk about energy communities, which is a very successful, I believe, very successful concept in Austria. It's very similar, or at least they might become all microgrids. They're focused on PV at the moment, but there are 4,000 almost of them. And he will talk about his research that he's doing. Michael has 7 years of experience working in China, in Kazakhstan. He was also in Venezuela. He has a lot of experience in establishing and developing companies in other countries, experience in developing greenfield and brownfield projects in management, project management, biz staff, technical and technological development, and in renewable energy. So I'm very interested to hear about your topic here, Michael. So please go ahead and tell us a little bit about your research project here. Thank you.
Thanks a lot, Michael. Thank you for the introduction. Thank you for the invitation and giving me the chance to talk in Xendee University Week today. My name is Michael Niederkofler. I am the head of the Innovation Lab Cells for Energy, and just starting into the presentation to give you an overview about this program. We are part of an initiative of the Austrian Ministry of Innovation, Mobility and Infrastructure, which is conducted in the form of public-private partnership. And these are regional energy system transition labs. There are 6 all over Austria. You'll see on the left the map of Europe. Austria is quite in the center, and there are these 6 system transition labs. We would like to really call them transition labs, although there is research done in these programs, in these initiatives, but the focus is really to promote the transition to advance going towards 100% renewable energies. So what's our energy system transition lab all about? We go under the name of Cells for Energies, and we were thinking, how can we advance the topic of energy communities? As Michael said in the introduction, that's a system that's been established in Austria for a couple of years, which is very, very successful, but it is not telling the whole story. So we were thinking about how can we advance this, how can we go beyond just integrating electricity. Specifically, it's mostly PV that is integrated in these energy communities. How can we bring it to the next level? And here you can see on the right the map a little bit. We are in the eastern part of Austria, mostly on the province of Burgenland, covering a region with about 200,000 inhabitants. And our main areas of interests are sector coupling. We look into heating and cooling, which I will give you a couple of more details later on. We look into the application of hydrogen. And most of all, we think about what is the systemic impact of energy communities? How can we integrate this model fully into the energy system? And also, how can these regional energy cells, like that we like to call them, how can they provide system services? So we're looking into a future where there is no fossil energy generation anymore. There are no big power plants fueled by gas or coal or oil, but these plants provide a lot of services, and they have to come from renewables in the future. And that's one of the core topics that we look into. So what I'm talking about here, we're talking about a transition from the left to the right. On the left side, there are some core properties of fossil fuel energy systems. It is generated mostly in central power plants. We have a rather low share of electrification at the moment. We can do the load balancing on the generation side. There is no need for sector coupling. Transportation, heat, cooling, electricity are mostly independent in a fossil fuel energy system. The energy prices depend mostly on the price of fuels, which are settled on the international energy markets. And then we look on the right, that's where we want to go to a fully 100% renewable energy system, and we see quite stark differences. Instead of a few central power stations, we will have many decentral power stations. For Austria, for example, we estimate that we will need somewhere in the ballpark of 1 million PV plants in Austria, and that's about 2 orders of magnitude more than the number of power plant installation today. With this additional PV and wind, naturally the share of electrification will rise dramatically. Models predict that the electricity share in the energy mix will be above 60%. And we will have an energy system where the generation is not stable. It will rather follow the sunshine, the wind, the water levels. So we have volatile generation, and we have to keep the load balancing on the demand side instead of the generation side. And because all of the energy system will be electrified, the electric grid will play a very important role, and sector coupling will become a necessity, or is a necessity, in a 100% renewable energy system. And this transition doesn't go by itself. There is a bottleneck symbolized here in the graphics, and it's not only one bottleneck, there are a couple of bottlenecks that are there on the way to this transition. We need invest in electrification. We need more flexibility. We have to establish decentral ancillary services. There are regulatory hurdles. The grid capacity needs to be increased, and of course there are also conflicting economic interests. So it's not always that all stakeholders pull in the same direction. And what we are looking into, where the research of our project is mainly focused, is how can we overcome these hurdles? How can we go through these bottlenecks? And the system that we propose, we call it energy cell. And the idea behind that is that energy cells are complete regional energy systems. They are not just looking at electricity, and they are not just looking at energy generation on balance. They look to be able to provide locally generated energy that is locally consumed on all time scales. For this, we need long-term storage, we need flexibilities, but we also need grid forming, and we need the capacity to form a stable grid. These energy cells, however, they are not islands. They are considered to be connected to the overall grid, connected to each other via standardized interface, where they communicate with energy markets, flexibility markets, and markets for ancillary services. And the keywords, or we think about the key items behind them, is regionalization, electrification, flexibilization and sector coupling, and decentralization. What are the key features? Key features, as I already mentioned, in this system is that we have local renewable generation that matches local renewable demand on all time scales, that we are able to manage our regional energy resources within the system of this energy cell. We have standardized interfaces connecting to the overarching and already existing grid. And on the non-technical side, it's also very important that all stakeholder requirements, be them economic, legal, or social, can be taken into account. And there are also governance and organizational structures in place that allow for effective management of these interconnected energy cells. So energy cells are not energy islands. They are designed to be able to not only connect to, but integrally support the overall energy grid and provide also the system services and the stability that is needed to have a grid that is running 100% on renewable energy. And in the end, we envision a web of cells, if you want, of these energy cells, all connected to each other, where each of the regions that forms such an energy cell is not the same. Renewable energies are not the same everywhere. You have areas where biomass plays a big role. You have areas where there's a lot of wind potential. You have areas where hydropower plays a key role. So each of these energy cells is designed to play to the strengths of the region, and they are connected to each other and form an overall Austrian European energy system. I'd like to mention here that this representation is rather an organizational concept. It's not a physical one. We will still use, of course, the existing power grid, but the usage pattern and the organization pattern will be organized quite differently in this concept. Digitalization is the key to make this happen. So in our project, we have a very strong focus on developing the digital services. Don't have too much time to go into the details here, but as you can see in the center, this green box is where all the services are being developed that are needed to manage these energy cells. One of the most important ones is our multi-energy virtual power plant that acts as a director of the system and relies on the provision of real-time data, because of course we need to know every time what's going on in the system to react, to activate flexibilities, to manage storage systems, to do demand response schemes in order to make sure that generation and demand is always balanced. And in just as a closing slide for talking about our energy cell system, this is operated as a living lab. It's not something that is done for just a single project once. Rather, we build the whole infrastructure for the design and operating of these energy cells in the region that I've shown before. And there are already 8 different research projects making use of this living lab infrastructure, making use of the systems and the infrastructure that we build up. And there are about 2,000 energy community members part of this living lab. They are organized in 21 energy communities. We have 13 rural municipalities and 1 urban center as partners in the living lab, more than 50 companies, more than 50 municipal facilities, and more than 70 companies participating and playing a role as a customer, as a stakeholder, as a provider of infrastructure and participant in the research and in the developing of this approach to the energy transition. One item at the end of my presentation, one item today I would like to focus on is renewable heating and cooling. Here you see a presentation that presented the numbers of energy consumption in Austria as it was in 2023, and private housing takes up about 1/4 of the energy demand in Austria, and the majority of this energy is used for heating and cooling. And this makes it evidently clear that if we want to head towards a 100% renewable energy system, that heating and cooling has to play an integral role and a vital part of this equation. In a prior project, For this reason, we looked at renewable heating cooling within these energy cells. There's a table that shows you some scenario simulation that we did. And without going too much into the details here, I just want to point out that in this scenario, we replaced all fossil fuel heating and cooling, as well as all combustion vehicles for EV, and we looked at the results. But it was done for a community with about 3,000 inhabitants. And again, without going too much into the details, these are the results of the simulation. We would need about 3 megawatt additional wind power and 8 megawatt hours additional electric battery capacity to support the electrification of the heating system. And these results exceed the current installed capacity by a factor of 10 to 100 in some cases. And it's really not feasible to achieve these results with just pure electrification. So we had to find another approach. We had to look somewhere else and think differently and think about where can we get the energy for heating and cooling from, what can we do to achieve our goal in this respect. And that's the focus now of the Cells for Energy Living Lab. We are looking into energy networks. These are low temperature heat distribution systems that exchange heat and cooling at near room temperature levels. So they are very efficient, and they use decentralized heat pumps to tap into this grid resource, into this energy grid, and utilize this for heating and cooling. This results in a maximum energy efficiency. This allows the cross-sector utilization of heating and cooling because these decentral heat pumps act as sector coupling units, and this allows for a high integration of renewables into the local energy system. So how do you go about into developing such a network? We did the exercise for an existing residential area in one of the towns. Stegersbach, it's one of the towns that are part of our living lab. And we start with an assessment of the demand and an analysis of the heat demand density to evaluate how can this be built and also how can this be organized. Can we use energy communities as an organizational envelope to operate not only electric grid and participate communally on the electric grid, but also use this for a heating grid. And here you can see some of the results of the heat demand analysis. We went through the whole area where this energy grid is intended to be developed and deployed. And you can see there are some buildings that have a very high heat demand. You can see the picture, that's a sawmill. It has quite bad building insulation and low heat demand. On the other hand, the existing residential area has a much lower heat demand, but to do this meticulously is very important to get the clear picture what kind of energy amount per year and at what time, how the load profiles do look like. So that was the result of this analysis. And based on that, we then developed the actual engineering or the basic engineering. The detail engineering will be carried out this year. But you can see we find the different locations for the Earth's probe fields, where we go into the ground, tap into the geothermal energy or the heat energy of the surrounding environment. On the one hand, we also tap into heat by burning biomass fuel, and we did an investigation to use waste heat from the wastewater treatment plant, and all these energies, these heat energy sources combined provide the energy for this low temperature energy grid that is then distributed in these residential areas. And the neat part of that is that each of the houses has their own heat pump. So they are also rather independent. And with this decentral sector coupling unit that we have in the form of heat pumps, we can match this, we can map this to existing energy community structures on the electricity level and match the electrical structures on the heat side. And this will be something that we very interesting to see how it works out. This project is set up and will be up and running by next year, where we will be getting the first results of this integration of an energy network into an existing residential area with an existing energy community. So what are we expected? We expect that we, in the next year, will be able to validate the concept, that we can identify the high potential renewable sources. As I said, we will tap into various sources from geothermal, wastewater, but also biomass. And we will get a heat demand model for the various technology scenarios in the existing buildings. And of course, as I said, that one important result should be this heat electricity combined energy community, where people communally produce energy, communally use energy, and we have in the center of this community the sector coupling from electricity to heat and vice versa. And yeah, we're looking forward to switch on the switch in the next couple of months and see if the research and the development and the engineering that we did so far will pay off, and it will be a lighthouse model for any future renewable energy projects, not only in Austria, but all over Europe. And with this, I'm coming to the end of my presentation. I hope you could all have taken away something from it. And I think we might have even a couple of minutes left for some questions.
Thank you, Michael. And there are some questions in the Q&A, and I have also a couple of them. So let's see if we get a couple of them done. Before I go to the ones in the Q&A, from a strategic perspective, the interest for these communities, how you manage these cells, right? Because when we have a microgrid in the United States, we mostly optimize this in terms of costs for the owner of the microgrid. So it's a single entity. But it seems to me that these energy communities or cells are basically built up with multiple stakeholders. So who is managing that system on behalf of whom? And how is the utility involved in this? Because I suspect that's a little bit different than we do it in the United States, right? So maybe you can speak a little bit to that.
Mm-hmm. Yeah, so for the management, as you, I think, gathered from my presentation, the technology behind it is rather complex, and energy communities are citizen-driven organizations. So they usually lack the knowledge and the expertise. So we as Enlion, we are one service provider for the management of such communities. And the energy communities will hire us to manage these grids, the digital system, all the management, the accounting, the measuring, and so on their behalf.
Yeah. Okay, sorry. I think we have to leave it there, because there are also questions in the Q&A, and I will pick just one, and then we will send you the rest of the questions with email. Okay. One question which probably is easy to answer is, these heat sources, do we have a central buffer or a distributed heat buffer?
We have distributed heat buffer in this project.
Yeah. So I would have had more questions, so we will follow up and also send you this, Michael. And I want to thank everyone for attending this session. We have to switch over to a new Zoom link for the next presentation because it's a little bit decoupled from this one. So thanks again, everyone. Thanks, Michael, and see you in 5 minutes on the other Zoom link. Thank you.
Thank you.